grades have been posted. You should be able to see it on Canvas right now. If you have any questions, please talk to the person who actually graded your homework. They'll be able to help you out. Any questions about homework 1 or any questions about the grading? Yes?
Well, we have a histogram of the grade.
Okay, I'll do that in the next class. Yeah, I mean, I don't think the individual homework scores matter so much because just to remind you, each homework counts for about 6% or something of, is it 6? Yeah, 6% of your final grade. So 1 point in your homework is 0.006%. I just want you to keep that in mind. I'm not saying anything else about that, but I just want you to keep that in mind. Did you have a question?
Yeah, I was going to ask, as far as grading goes for the homework 2, on the algorithm part, there's going to be, I was kind of curious how they're going to grade it, if they're going to be looking at our code, or because our hyperparameters can be so different.
Right. So the one thing, let me just repeat your question. Do the actual learned functions matter, or does the code or the actual implementation itself matter? Frankly, I don't care about the function that you produce, the hyperparameters or the weight vector or the tree in the previous homework. What I do care about is the performance of your classifier. Okay. And that you have followed correct experimental procedure. Okay. Guys who graded it, maybe you might have something else to say, but what I'm hoping is that this system, the way we are trying to set it up, if you make mistakes that do not affect the final output, it's not as bad. So the accuracy counts more than anything else. We will look at your code, I'm guessing, because it's important that you did not just submit a bunch of print statements, and you did something reasonable. So that's more important. Okay. Are there other questions about homework 1? Actually, there was one consistent question that came up. Grad students noticed that your final score was added up and divided by 1.1. That's because we wanted to normalize your scores. If you counted the number of points that were available for grad students, it was 110. So because you're grad students, we expect you to do 10 to 25% more. In the next homework, there might I don't remember how many extra points there are for grad students. So every homework will have extra questions for grad students. We'll scale it down to 100. Okay, so that's announcement number 1. Number 2 is about homework 2. That's due on Thursday. I hope you guys have started. And I also hope it's not as intensive from a programming point of view as homework 1 was. It's more work in terms of running things because there are way too many things to run, and you can just put a for loop and get done with it. Are there questions about homework 2? I noticed there was a lot of discussion about it on Canvas. Yes.
I want to ask about the shift data.
The what data?
The random.
Okay.
Shift order. So we just random for one time and use it for all. I mean, because every time when I run my program, I get different answer because my data is random.
So hold on. I'm a little confused. There are 2 sources of randomness here. One is the initialization of the weight vectors, and the other one is if you're running the perceptron algorithm in batch mode, you might shuffle at the start of each iteration. So there are 2 sources of randomness.
I mean the shuffle.
Shuffling. Shuffling, you should not. It's important that you shuffle at the start of each epoch. Yeah. But
so every time when I run it's
so
different.
Then the next question becomes, what do you mean by the answer is different? Are the weight vectors different? Probably they are.
Yes.
Is the predicted accuracy different?
Yes.
Is it wildly different?
A little like 5%.
5% is a lot.
Yeah.
I would say check your code, and is this for one iteration, one epoch, or multiple epochs?
Multiple.
Okay, then check your code. And if it still doesn't work out, then what I would say is run this over multiple trials and report the mean and standard deviation. I do not expect that to happen, but if it does, then report that.
So is there, you mentioned that it's going to be a lot of it based on the accuracy.
Right.
Is there a range that we want to
High.
hit? Just again.
High. It's not like, if you get within 80% of what this magic number I have in mind, you will get the points, will be reasonable. I mean, we know that there's randomness here. We know that multiple runs of the program can give subtly different, but not wildly different answers. So, it's not, the more important thing is that you've done the right thing, rather than you get exactly the right answer up to the 18th decimal place.
Okay.
Yes.
So with regards to the random weight vector initialization, could that have been a hyperparameter
So, okay,
instead of randomizing it?
Yeah, many people ask that question or related questions. So, couple of things to mention here. First of all, technically speaking, randomization would not be needed for the perceptron. So, if you want to give yourself a sanity check, you don't have to report it, but just initialize at 0 and see what happens. Okay, that's one thing. The second thing that I mentioned is all your weights should not be the same random number. The reason I ask you to do random initialization is because it does not matter so much in perceptron and SVM and such algorithms, but eventually if you guys after you're done with the class, if you go out and implement some neural network kind of things, their initialization matters and randomness is important, and you should not initialize every weight to the same random number. So you need to draw a random number separately for every instance. And a few people had asked questions, what range should this initialization be? My recommendation would be pick small numbers, pick random numbers between -1 to +1, or minus 0.01 to plus 0.01 or something like that. Does that answer your question?
Yeah, and basically since there's so many elements in the vector, you would just have a lot of hyperparameters.
Yeah, it's not a good idea to start it off as hyperparameter. Typically, in cases where learning is not guaranteed to converge to the global minimum of some objective, the initialization is not a hyperparameter, but the initialization itself can be the output of another learning step. So if you have thousands of hyperparameters, then that's really learning. Was there another question at the back? Yes.
Yeah, is it, when I did when I implemented the simple one, the first one just has a learning rate, it was doing really well. In fact, it was like, if I had it at like 0.5 or something, it was doing 100% accuracy on the test cases. And then when I implemented the margin, it like dropped down to like 60%. I tried a bunch of different hyperparameters, and I was just constantly getting really bad results.
Okay, check for bugs.
Yeah.
The margin perceptron typically does better. So normal perceptron is an instance of margin perceptron where margin equals 0, right?
Yeah, if I set the margin to 0, then it goes back up to the values that I was getting.
So what values are you iterating are you testing?
I just was doing informal testing. I implemented cross-validation.
But what ranges? What numeric ranges?
What?
I
I tried like 1, 2, 3, 4.
Pick
5.
small number. Just try numbers smaller than 1.
Okay, I think I did try like a 0.5 as well, but
Okay.
it didn't seem like it was working.
Look for bugs. I don't expect that to happen.
Okay, that was really what I was trying to figure out.
Were there other questions? Yes.
So for cross validation to pick a set of optimal hyperparameters, what do we use as performance measure of our
Accuracy on the validation set.
So what is the use of the number of mistakes percentage?
Oh, that's just for in the report. Are you asking about?
No, it's just in general.
So the number of mistakes is just something for you to report, mostly because I want you to notice how this behaves with respect to the expected mistake bound. You can compute the perceptron mistake bound for this data, almost. So at least as a function of dimensionality. So now it will be an interesting thing to think about, assuming that the margin is some constant. how does the number of mistakes behave with respect to increasing dimensionality? That's really the goal of this experiment. Not so much it's not a tool for deciding things in cross-validation. Other questions? Yes.
I think I was somewhat confused on like, you asked us to find a number of errors and a weight vector after one iteration,
Yes.
right? And that's not our final iteration for that, correct?
Say that again. What do you mean by that?
That's not the final weight vector that we would then use for prediction.
No, what do you mean?
To predict on the test set.
So you have two questions, right? One is just run one epoch. And
Well,
then,
I think it's like the second part of the experiment
yes.
where you ask us to run, you basically go through one iteration.
Yes. One epoch, basically.
Okay.
Yes.
And then, find the number of mistakes that you made during that one iteration and also the weight vector. And this weight vector is not the weight vector that we would then use on the test set.
No, that will be the weight vector that you use. Why won't you use? I don't. Is there something in the document that says you won't?
Well, don't, during the session, we go through it once.
Yeah.
And then we go through it again.
No. So okay, I see your point. The standard perceptron is the version that you generally use in production is the one where you iterate over data multiple times. This is just as a sanity check to see what happens at the end of one epoch. That's all. It's got nothing to do with. The question 3 asks you to do this over for multiple epochs. The question 2 is just run it for one epoch. In fact, I don't remember if the document says it. Don't even shuffle it. Just use the order that's there. Run it for one epoch. See what happens. If all of you have implemented the same version of perceptron, except for changes in hyperparameters and initialization, you should get the same accuracies at the end of the one epoch because there's no change in the order of examples. That's it. That's the only. It's just as a mostly for to make sure that what you have actually runs and you get some out. Yes.
For number 3, do we have to report on each hyperparameter for each data set?
Please don't. That will just give way too many numbers for us to stare at.
You don't want the weight vector for the 100?
Absolutely not. Please do not print the weight vectors. I know you're not submitting written homeworks, but think of all the virtual trees you'll be killing. So please don't print weight
I
vectors.
hand wrote it and I scanned it, the 100 weights.
Okay. Well, okay. You seem like you have a lot of time. Okay, I think we're getting to diminishing returns here with respect to homework. Another announcement is about midterm exam. It's amazing, but we've already come to the middle of a semester. There's a midterm exam next Thursday in class, right here. So please show up. The midterm exam will cover pretty much everything that we did till next lecture. So up to this week. And it's going to be in class, it's going to be as long as we have the 1 hour, 20 minutes. And it's closed book. Any questions about midterms? About the exam?
You said next Thursday?
Did I say next Thursday? Yes, I said next Thursday. Not day after tomorrow. Yeah, that will be a bit surprising for me as well. Yes.
Well, we have an example midterm.
Yes, I'll put one up probably this weekend. Okay, if there are no other questions, right, one other announcement is about project proposals. I think all of you have submitted it. I'm starting to go over it, I'm not done. I'll send you comments about it most likely by this Sunday. If you haven't heard from me by this Sunday, just post a message on the discussion board and I'll tell you that I'm late. Alright, so I think let's continue. We've spent 15 minutes on announcements, so I think it's better that we get started with the lecture. And we are in the middle of online learning. We are in the middle of the Winnow algorithm. In the last lecture, we came to the end of perceptron and started looking at the Winnow algorithm, and I pointed out that the Winnow algorithm is very, very similar to perceptron. In fact, let's put it up. It's quite similar to perceptron except for this one part, which is the update itself. Other than this box here and the initialization, there's nothing much left, but it's got a similar sort of structure as perceptron. You initialize your weight vectors, and for every example that comes in, you make a prediction. The prediction step is identical. You just take the dot product, compare it to the threshold, and then take the sign. And if there's a mistake, then you update. The perceptron is an additive update algorithm. You guys have implemented it. You probably understand it really well right now. The Winnow algorithm is multiplicative, meaning every weight is upon when the mistake is made, the weights are not added or subtracted, but the updates are multiplicative. Every feature that's responsible for making a mistake gets promoted if the example is positive. Every feature that's responsible for making a mistake gets demoted if the example is a negative example. So we saw this algorithm in the last lecture, and the way I motivated this was, if you remember, I pointed out that the perceptron mistake bound is r square over gamma square, but when r is roughly a function of the dimensionality, so the perceptron algorithm makes as many mistakes, or the mistake bound of the perceptron algorithm is a function of the dimensionality of the data, which is pretty bad if you have millions of dimensions, millions of features. And what we want are algorithms that can only weakly depend on the dimensionality and instead depend only on the features that are relevant. And I claimed in the last lecture that the Winnow algorithm is such an algorithm. I didn't prove that claim, we just came to the description of the algorithm, and I claimed that Winnow algorithm makes a mistake, the number of mistakes it makes is only weakly dependent on the dimensionality and dependent more strongly on the number of relevant features. Any questions about this algorithm before we get to the mistakes? Yes.
So the features are numbers, right? They are not Boolean general.
Yes. So in fact, there's a mistake in the slide. For this version of the algorithm, the features are Boolean. If the features are numbers, then you do not, the update rule changes slightly. It becomes equivalent to basically doing an additive update in the log space. It's multiplying by e power y times xi. Okay, so now that we've seen this algorithm, and in fact, you know what, at this point you should be able to implement this algorithm because it's not terribly different. You can just, if you have the template for the perceptron, keep it someplace safe because you will be using that multiple times through the semester. It turns out that many learning algorithms follow generally a very similar template. You take an example, you do some processing, and then you update the parameters. So let me now derive the Winnow mistake bound. And to make life a little simpler, I'm not going to do it for arbitrary functions. I'm going to focus on the case where the true function, the hidden function, is a k-disjunction. Just to remind you, a k-disjunction is a function that is basically an OR of k Boolean variables. So the setting is we have n Boolean variables. Only k of them are relevant. We don't know which k. They are hidden from us. And the output of the true function f is true when any of those k are non-zero. And if all of them are zero, then the output is false, irrespective of all the other n minus k variables. And in this setting, we can prove, and it's actually not a really difficult proof, it's an interesting proof actually. We can prove that the Winnow algorithm can learn this class of functions making with a mistake bound of k log n. So if you remember, this is exactly the mistake bound that we had for the halving algorithm for Boolean functions for k disjunctions, and it turns out the Winnow algorithm realizes that mistake bound and is an efficient algorithm because rather trivial to implement. So just to point out, k log n means we are still not free of the dimensionality. If you have a million features, you still pay some penalty, but it's only logarithmic. Log of a million is a tiny number. The more dominant term here is k, the number of relevant attributes. And this actually was a fantastic paper in 1988. This paper introduced a lot of what we know of as theory for mistake-bound algorithms. And if you feel like you're interested in this or would like to read more about this, I would strongly recommend the paper by Nick Littlestone. And the title of the paper is Learning Where Irrelevant Attributes are Bound. So let me prove this theorem. This theorem is not terribly hard to prove, but let me prove it. But before that, before actually getting to the proof, a couple of things about theorem itself. The way you read a theorem is you stare at it and savor it without actually jumping into the proof, because sometimes the proof can mess things up. So you see the theorem and you try to reason about what it implies. I just pointed out that it's only weakly dependent on the features and more dependent on the number of relevant attributes. So this kind of an algorithm is called an attribute efficient algorithm. And the nice thing about this kind of an algorithm is that suddenly now we are no longer at the mercy of the dimensionality as much as we thought. So we can try out features. Let me just throw in buckets of features into the problem and hope it works. And this is often the strategy that's used in natural language processing, for example, where the dimensionality is literally, where the number of features is literally of the order of millions. As a side note, it turns out that in practice, many of these algorithms work just as well. I mean, perceptron and Winnow, and it's not clear why, but theoretically, we have these mistake bounds. So, before we get into the proof, any questions about the mistake bound theorem? Yes?
So does this proof only explore this functions?
This statement of the theorem is for k disjunctions, but the property about Winnow is generally true. It's attribute efficient. It's only weakly dependent on the dimensionality. The version of Winnow that I've written talks about Boolean functions, and for k disjunctions, the proof is not terribly hard. Which also means I'm going to step through the proof and show you all the gory details. It's not terribly hard, but it still takes about 4 slides. So let's just to get the stage set for the proof. What we're going to do is, just to remind you, we are going to prove that for this class of functions, k disjunctions, the Winnow algorithm will make only k log n, order of k log n mistakes. And to show this, what we'll do is we'll separately count the number of mistakes this algorithm makes on positive examples and the number of mistakes it makes on negative examples. The total number of mistakes this algorithm makes is just the sum of these two things. We'll add those up, we'll bound each of them separately, and that will give us the bound. And just a word about notation, I'll call the mistakes that the algorithm makes on positive examples m plus, and the mistakes the algorithm makes on negative examples m minus. Are you on board with the general strategy of proof? Does it seem reasonable? Okay, I'm going to take that as a yes. So let's talk about positive examples. And it's going to there are some very subtle arguments that show up in this proof, so I want you to kind of play this as if it were some logic puzzle. So, first of all, remember that our function is only the class of, is a k disjunction. And I'm going to claim that the update rule, which let me remind you of the update rule, which says wi And this is, well, in fact, so this is the update rule for mistakes on positive examples. If a feature is 1 and a mistake has been made, the weight will get doubled. And first puzzle is a mistake on a positive example. Every mistake on a positive example will double the weight of at least one relevant feature. Why? Yes?
A relevant feature has to be positive in order for it to become positive.
Yes. So we know that it's a mistake on a positive example. The true label is +1 or true. What made the true label positive? The function's a disjunction. There must have been at least one input feature that was true, relevant feature that was true. So just by virtue of this update rule, there must have been at least one feature whose value was 1. So at least one relevant feature will get doubled on every positive update. Okay, so that's easy. The next thing to note is we've initialized, remember that, and this aspect becomes very important in the proof. We initialized our weight vector with the vector of all ones, and our initial threshold that each example had to cross to become positive was the number of dimensions. Now we fixed it to n, and now the question is, for any relevant feature, how many times could it possibly get promoted? Remember that promotion is doubling.
Something like log n.
Something like log n. Why?
Because we have to double it until it crosses the threshold or something.
Right. So we remember that we will double the weight of each feature only when there's a mistake on a positive example. Let's say the weight on that feature crosses the threshold. Then the sum is going to cross the threshold, so that you'll no longer make mistakes on the positive example. So you will stop doubling the weight on any feature that's relevant if its weight crosses n. How many times can you double to reach n? It's basically just log n. In fact, it's log n plus 1, but that's okay. At most log n plus 1. After that, you'll cross the threshold and you'll never make a mistake. For any relevant feature, if the weight associated with it crosses the threshold, then you'll never make a mistake on that. So you'll be, so number of promotions for any relevant features is at most log n plus 1. But this means we have a bound on the number of mistakes on positive examples. Remember that we are only talking about positive examples. There are only k relevant features. In the worst case, in the absolute worst case, every relevant feature keeps getting doubled independently, and so the number of promotions you make is k times 1 plus log n. So the number of mistakes you can possibly make on positive examples is at most k times k log n, basically. Is this argument okay? Questions about this? Yes.
Just to reiterate, this is the maximum amount of mistakes that will make the K. That's most adversarial.
Yes, it's the most adversarial. It's possible that
It will be less.
It might be less if this style of analysis appeals to the union bound, where you just consider all these different cases to be independent. In the worst case, they are all independent, which means this is the maximum it can possibly have. So we'll actually use this number later on for counting the number of mistakes for negatives. So I want you to be comfortable with this before we move on. Yes?
Could we, like the same element of the weight vector, could it be from prior examples, could it be divided in half and then on subsequent examples we double it, so it kind of oscillates back and forth.
That's an excellent point. In general, possibly, but we have k disjunctions here. If an example occurs, if an example is relevant, it keeps going up, right? Because it's you can, so let's sorry, not an example. Let's say a feature xi is relevant. Now, there are two possible things that can happen at any point. Either at some point when there's a mistake, either the feature gets promoted or the feature gets demoted. And I'm going to argue that because xi is a relevant feature, it will never get demoted. Why? Because if demotion happens only on negative examples, only on mistakes on negative examples. Xi is a relevant feature, which means its existence in the function means that it's never associated with negative examples. So by construction, at least for this function, for relevant features, they keep going up, hit the ceiling and stop. For irrelevant features, they can go along with the ride. When the positive example is promoted, there might be irrelevant attributes that get promoted, and those can oscillate. So the next thing we need to do is bound that, the number of times it oscillates. But that's a good question actually. Any other questions? So I have to confess, the first time I saw this proof, I was thoroughly confused. So if you're not confused, then you're way better than me. So that's also an indication that you should probably go home and try to convince yourself that I'm not lying to you. Not about me being confused, about the proof. So let's now look at negative examples. So we have a bound on number of mistakes for positive examples, and we know that it is k times 1 plus log n. For mistakes on negative examples, we're going to use a totally different strategy because of the point that you made. Negative examples, the weights, it turns out, can go up and down, so we can't just easily bound it. Instead, we are going to use a slightly more convoluted strategy to get a mistake bound. To do that, we're going to count or keep track of the total weights, meaning the sum of all weights in the weight vector. So I'm going to define this quantity called TW of t, which is simply the sum of all the weights. I can keep track of it, right? At any point given a weight vector, I can just add up all the elements in the vector, and let's see how that moves as updates go along. So to start off, TW will be equal to 1. It will be equal to n. Why? Because by design, I have mandated that all the weights should be 1. We have n such numbers, you add them up, you get n. Also, and this is important, because we are only multiplying and dividing, and we are only multiplying and dividing by 2, which is a positive number. We started off positive, we are only multiplying and dividing by positives, so the total weight can never be negative. Right? Okay, so these are just axioms, and we'll use these as the base case in our recursion. Let's now think of what happens to this TW when you make a mistake on a positive example. So let me try to write this down, because this is not one slide of material. So remember the TW at t is the sum of all weights. An example comes in. I'm going to call this x. And let's say x bar is a vector which consists of it's a Boolean vector of n dimensions, and it comes with a label. We know that it's a positive example, so x comma plus 1 comes in. And so how do we make a prediction? We'll first take the dot product of sum of xi wi. If it is greater than or equal to theta, which is equal to really n, so I'm just going to put n here. then plus, else, minus. This is our prediction rule, and we made a mistake. What this means is we know this is not true. We know that sum of xi wi is less than n. Okay. Now let me divide this input vector x into the elements of this input into two parts. Things that are relevant, features that are relevant, and features that are irrelevant. We don't know the true function, but we can still partition it, right? So this means that this is sum over xi in relevant plus sum of the relevant weights and sum of the irrelevant weights is less than n. Okay. Now we made a mistake because it's less than n. And what we do is we just double all the features that are in the input. Right? So we partition this, we partitioned it into relevant and irrelevant. We can also partition as in the input and not. We double all the ones that are in the input. So let me actually erase this because I'm running out of space. So what we know is the dot product is less than n, and I'm going to partition not this sum but this summation into relevant and irrelevant. And when I make an update, TW at T is xi. In fact, let me not do relevant and irrelevant, because instead of that, let's think of all the features that are in the input and all the features that are not in the input. And I'm going to partition the I into two parts. Is this partition clear? Forget the relevant and irrelevant part. I'm just partitioning this summation into two parts. There are some weights that correspond to elements that are in this example. There are some weights that are not in this example. Now, let's think about this summation. The sum of wi xi is simply the sum of all weights such that xi in x. Why? Because each xi is plus 1 or is 0 or 1, and only those xi's that are equal to 1 contribute to this dot product. Do you agree with that? So, is this statement correct? Okay. And when we double the weights, we'll only be doubling these weights. Each weight that occurs in the input, each weight that occurs in this particular input that corresponds to a feature in this input, we'll double it. So basically the total weight at t plus 1 is twice plus these guys don't get touched according to the update rule. Right? Ask me a question.
When's your birthday?
Ask me a relevant question. Relevant questions is important. Okay, but at this point it should start to get clear. You double this part. We know that one of them is less than n from this. So this is less than n plus the rest of it. The rest of it is just TW of t. Let me remove this. I see that now. So we know that this guy is less than n. One of them. If you take away one of them, the rest of it, the sum over wi relevant in x plus sum over wi not in x equals the original TW, right? Just by definition here. And so basically TW is this blue box plus sum of wi. And this guy is less than n. So it's TW plus n. So let me clear this, and what we get is TW at t plus 1 is less than, the total weight at t plus 1 is less than the total weight at t plus n. Now at this point you are confused. Yes. So
I'm still having a hard time where the n came from.
the n came from the algorithm. So remember the
Right, n is your number of dimensions.
you initialize theta to n. So the n comes from this place here. You initialize your threshold to n, you fix it, you never update it. Notice that nothing in this part here talks about updating theta. So your prediction, and you predict using sign of w transpose x minus theta, which is simply wi xi. You use this test to decide whether the output should be positive or not. But theta equals n.
Okay.
So really it's this. So let me just quickly summarize that the statement that I made. Right. So what we had, so TW at t is sum of wi, and given some example x is x1, x2, xn, n-dimensional example, you split it into two parts.
Relevant number.
Things that where xi equals 1, and here you say xi equals 0. So you get one set here and another set here. These guys don't contribute to the dot product. These guys will disappear because they don't contribute to the dot product. So the only things that contribute to the dot product are these. So effectively, the dot product is simply the sum of wi such where xi equals 1. Right? So these are the only guys that get doubled. The rest of them remain as is. So you have two copies of weights in your total weight. You have two copies of those weights that get doubled, and you have one copy of the original weight. So you have you have some weights for these case, and they don't get touched because the update rule does not affect them. And these things get doubled, and so you get plus. Because we made a mistake on a positive example. Part of the stuff that got doubled and n, and we have a less than or equal to. I see now that it looks much cleaner on my notes here than in the projected stuff because it seems like a total mess up there. So I'm going to ask you to take a look at this again. Go over it and convince yourself this is true. All you have to do to make this proof work is to partition the weights into two parts. Weights that are relevant, weights that are irrelevant. Only the weights that are relevant get promoted, and then you just count, calculate the sum. And you can show that the total weight is will not grow more than n at each time. But what this means is, let's consider the total increase in the total change in this TW. So TW at t plus 1 minus TW at t is less than n. of numbers. Right? And
I thought there can also be equal. Can it be?
the counts will be equal.
I mean the less and the equal.
The counts will be less than, strictly less than.
Why?
Because we predict positive if it's greater than or equal to. We have made a mistake on a positive example, which means we have predicted negative, which means it's not greater than or equal to, which means it's less than. So we predict, the prediction is +1 if we have made a mistake on a positive example. The true label was plus, but our prediction, this was the true label, but our prediction fits this category, which means it's less than, and we know this is equal to n. And so that's why this becomes less than. Okay, so if you know that the increase in the total weight can be no more than n for one mistake, one positive mistake, and we have assumed that the total number of positive mistakes, not assumed actually, we just denote the total number of positive mistakes by m plus. M plus is just the number of times you make a mistake on a positive example. Each time you make a mistake on a positive example, you can grow the total weight by no more than n, so the total increase that can happen can be no more than m plus times n. Every positive mistake, it can go no more than n. You make m plus positive mistakes, so the total increase can be no more than this quantity, than the product here. So that's only about positive examples. Really the difficult part, the reason we are getting there through this process is to worry about negative examples. What happens to the total weight when you make a mistake on a negative example? Intuitively, will it increase or decrease? Decrease. Because you are dividing some elements of the weight vector. Not all, but some elements of the weight vector. And using a similar sort of a messy argument, you can show that the total weight will decrease by the resulting total weight will not be more than, or will be less than the original total weight minus n by 2. And it's basically exactly the same argument. You partition the weights into two parts, things that are in this example, and you partition the weights into two parts, yes. One part corresponds to features that are in this example, and the other part corresponds to features that are not in this example. Only the features that are in this example, by design, will get demoted. So all those weights will go down to a half, and now you count the total weight. So the new total weight will be less than original total weight minus n by 2. Same argument, and I encourage you to try, not encourage you, I insist that you work it out yourself. It's about 3 lines of proof. Okay, so if every mistake on a negative example leads to a decrease in TW of less than n by 2, then the total decrease is simply the number of mistakes you make on negative examples times this quantity. Okay, so now comes the more interesting argument. So let's now think about what range this TW can ever be in. We know that TW can only be positive because we start off with positive numbers and we multiply and divide by positive numbers. So let's build this inequality. 0 less than, at any t, 0 is less than or equal to or less than TW of t. Now this will be less than the initial total weight plus the maximum increase that can possibly happen, which is m plus times n, from here plus minus the maximum decrease that can possibly happen. And we know that this guy equals n. So really 0 less than tw of t n. So at any point of time for any t, the total weight will be more than 0 and it will be less than what you started off with plus the total number of mistake, the total number of the total increase minus the total decrease, right? And what is interesting about this is the left and right side of this inequality is independent of t. So we can just now we can compare these two quantities and it's independent of t, and that gives us an inequality that relates m plus and m minus, right? And this is cool because we've already got a bound on m plus. So we know just by rearranging this and doing some algebra, we know that m minus will be the number of mistakes on negative examples has to be less than roughly twice the number of mistakes on positive examples. And the intuitive, this is just, it's okay to prove it, but here's the intuition. For positive examples, you keep doubling every time. What you do is you keep doubling and you hit the top. Once you hit the top, you're done. You never decrease for the positive examples, right? For negative examples, it's possible that you may keep increasing it. So you can make at most m plus increases and then you will bring it down. So you basically go all the way up to the top and then bring it down. That's just a very rough intuition. It's not technically very fully correct, but what this tells us is really there's this limited span of increases and decreases and you're counting how many steps it takes to go through this. It turns out for positive examples, you're doing roughly log k log n updates. And for negative examples, you're doing twice that much. So just to summarize this discussion, what we know is the number of updates on positive examples is less than 1 plus log n. The number of updates on negative examples is less than twice 1 plus m plus. The total number of mistakes is simply the sum of these things, which is you just add them up and you get roughly a term that is k log n. That gives us our mistake mark. This took a little longer than I had planned, partly because the proof is kind of a little messy. But are there questions though? This is not a very difficult proof, and if it seems difficult, all you need is to stare at it again. Not just this step. Yes?
So I was a little uncomfortable with the last part of the inequality, how you said it's always less than or equal to, an initial weight, some weight plus, something, and then minus something.
Mm-hmm.
It seems like you couldn't say that necessarily because you're subtracting off something.
That's interesting. So let's go back to that step. So what we know for sure is this quantity here is the total increase that can ever possibly happen. And this quantity here is the total decrease that can ever possibly happen. Right? At any step, so m plus and m minus are just the limits, the total number of mistakes in the limit. But at any time step, the total weight cannot be, you start off with some quantity, you add something to it, and we have a bound of how much you can add. You take away something from it, you have a lower bound of how much you can take away. Right?
But let's say that you take away first.
But we have a lower bound of 0. So you can't keep going below that.
Right, okay.
And in fact, another way of proving this is just by stacking up all these TW things and telescopically cancelling things out. So you can also you can list it out as TW0 equals n. So the telescopic summation might look something like this. So TW0 equals n. If the mistake on the positive example and at any point TW T this is not going to be, I have to draw a whole branching thing because the order is not given to us, but you can actually cancel this out telescopically and that will, the argument works. Because there's a lower bound of 0, we are okay. Other questions? Things that are more basic than the, I saw you first and then I'll come to you. Yes.
I'm still not clear about the upper bound.
You're not clear about this one?
No, the upper bound on total weight.
Huh?
And plus that k times n minus some. I'm not sure that minus would work. If we don't make a mistake on negative examples at all.
Then we'll never update.
No, but then the bound will not hold because there is no negative one.
Oh, but then m minus equals 0. Then this quantity equals 0. M minus is the number of mistakes you make on negative examples. So, if we don't make a mistake on negative, this is totally fine. These are very, very loose bounds. And these don't necessarily, they are correct in the sense of they are so loose that it's not going to be broken. Did you have a question? Yes.
I have one question. First, why the boundary should be n? I mean, why we can make sure when it's greater than n, we will never make mistake. Why is n, not other number like n over? Why is n?
Which one? Which boundary? Which?
Say theta. Why?
Oh, that's just by design. That's mostly to make the proof work.
So it's not only be n.
No, that has been chosen so that this TW starts off as n.
Yeah, why is n? Just a choose?
No, it's just it's an arbitrary choice that makes the math work out.
Okay.
Actually, the reason it's n is not for this side of the proof, but for the positives. Because the threshold is fixed to n, we can say that the number of mistakes is log n. The number of mistakes will be the log of the threshold. And if we fix it to n, it becomes log n.
Okay. So I don't understand very well about the mistake on negative example. Why it's less than 2?
There's a 2.
2 times 1 plus.
Oh, this quantity here, right?
Yeah.
So what you do is, okay, let's take this inequality. 0 less than n plus. So let me write that down on top so that we can. Right? We have that inequality on top. So now look at the first term and the last term here. So what we have is 0 less than n plus n minus n by 2.
Okay.
So this means 0 less than 1. I'm going to divide throughout by n.
Okay, so that's fine. Thank you.
And then you
Thank
then
you.
receive it. Okay, so in the interest of time, I'm going to plow ahead with the assumption that you guys are going to read this carefully when you get home, and then torment me with questions in the next class. What we are able to show through this proof, remember the statement of the theorem. That's probably more important than anything else here. The statement of the theorem is for the class of k disjunctions. This theorem shows that the Winnow algorithm will make no more than k log n mistakes. And in contrast, the perceptron algorithm will make order of n mistakes. So, if the true function is, so there's something that you should think about. If the true function is a k disjunction, there is nothing in the algorithm that uses k. There's nothing in the algorithm that says that, I know that my function is a k disjunction and I'm going to somehow use the k. The mistake bound just shows up. As when you are implementing the algorithm, the mistake bound does not matter. You just write down the algorithm, you run it, you don't even know if it's a k disjunction when you start off. It just so happens because the function is a k disjunction, you only make k log n mistakes. In some sense, the mistake bound is a function of the true concept space rather than any choice that you made during your run of the algorithm. Which means that you are basically discovering some properties of the data, or it does not depend on any choices, any extrinsic choices that you make. It's a property of the function, the difficulty of the function itself, which is important. We care about learning algorithms where only the parameters that are relevant for the function influence the learning complexity. So, just like perceptron, so let's step back and see where we are. We are again in the world of online learning, and we looked at the Winnow algorithm, and I pointed out that it's a multiplicative update rule, and we have the Winnow mistake bound, which says that we make mistakes, the number of mistakes we make is only weakly dependent on the dimensionality and linearly dependent on the number of relevant features. Just like the perceptron algorithm, let's look at a couple of generalizations. One important generalization comes from a problem that it's surprising nobody's noticed. We start off with positive weights, and we only multiply or add examples, multiply or divide each weight, which means the weights can never get negative, right? Which means we are restricting ourselves to a set of functions, set of linear classifiers that can only be represented, that only need positive weights, which is a strict subset of negative, of the set of all possible linear classifiers. What that means, for example, we can represent functions like this. So we have, this is two-dimensional, we have 4 points, 0, 0, 0, 1, 1, 0, and 1, 1. And we have 4 points here, and we have functions that are called monotone, which means that there is no negation. You have functions like x1 or x2, you have functions like just x1, just x2. The slanted line here represents x1 and x2 actually. The output is true when only this point, only the far point up there gets the value 1, everything else gets the value 0. So this point lies on the positive side of the hyperplane. So these kinds of functions are called monotone functions. Only functions, Boolean functions that do not involve negations. And it turns out that using only positive weights will only give us monotone functions. In particular, functions like these cannot be represented. So if you have a function like x1 minus x2 greater than 0, a linear classifier that says in 2 dimensions, a linear classifier that says x1 minus x2 should be positive for the label to be positive, the Winnow algorithm will never learn that function because the weight on x2 is minus 1, negative. We started off with positives, we never go to positive negatives. Did you have a question? Yeah.
Well, I guess one question, could we just double our number of features and have negative ones, like negate?
So if you start off with negatives, so let's say, in fact, that's really the answer. That's the trick that we use. But before we get into the answer to the problem, do we have questions about the problem? why does, so do you see why the Winnow algorithm can never learn this weight vector? Okay, the answer is pretty simple. What you do is exactly what you said. Let's say you initialize, for every variable xi, you create two copies of the weight, w plus and w minus. Effectively what you do is you initialize w plus with +1 and w minus with -1. And every time you make a promotion to w plus, you demote w minus and the other way around. And you pretend as if you're learning two functions simultaneously. One of them is the monotone function and the other one is its negation. And at prediction time, you add these things up, add the w plus or w plus minus w minus, and use that as your weight vector. And it's exactly the same algorithm, except you modify the update rule slightly. And I'll show you what the modified update rule is. But the thing to note is that if you have functions of this kind, where w pluses and w minuses are all positive, then you can produce any w. There's no restriction, because you can set w plus to 0 and w minus can be an arbitrary negative thing. So you can get arbitrary weight vectors. So the balanced Winnow algorithm looks like this. For every feature, you create two weights. So you have two weight vectors, w plus and w minus, and you instantiate both of them to all ones just as before, and your threshold is now still n. But the prediction step is different from the original Winnow. You make a prediction using the difference of the weights. So effectively, you pretend as if the weight vector that you produce at the end of this algorithm is the difference. You use that to make a prediction, and if there's a mistake, and let's say the mistake's on a positive example, what you do is you promote all the w pluses and you demote all the w minuses. So what you're saying is, this example was positive and this feature was in this positive example, we made a mistake. Let's blame all these features that existed in this example. All of them should be above the threshold as far as w plus is concerned, so let's make them big. And w minus is a weight vector that is supposed to represent its negation. If the true function is positive, then the negation is negative. So you blame the same features for making this positive thing, and you demote all of them. So basically what you do is you promote all features in w plus and all the features in the example from w plus, and all the features in w minus get demoted on positive examples. On negative examples, on mistakes on negatives, you do the opposite. Every feature that is in a positive example, every feature that's in this example, which is actually a negative one, gets demoted because you made a mistake. But only for w plus. For w minus, you do the opposite, you promote. It's a very simple modification of the Winnow algorithm, and this is called the balanced Winnow, and it turns out that anytime you actually anytime you have to use Winnow, you have to actually implement balanced Winnow, because this is the one that can represent arbitrary Boolean functions. So what's the problem here? Have we solved everything? We have a function classifier that can represent arbitrary Boolean functions and has this nice mistake bound that's only dependent on relevant features.
Still a linear classifier.
Okay, that's one problem, but we have dug ourselves very deep into that hole. We're not going to move out of there for quite some time.
We've not proven the mistake bound with the balanced Winnow.
It's going to be roughly the same, actually. It's going to be just slightly different, not too much. Actually, by doubling the weights, by keeping two copies of the weights, what are we doing? How are we possibly hurting ourselves? You're doubling the dimensionality. the number of parameters that you need to store becomes double. In k log n, that n term becomes 2n. So effectively this algorithm has a slightly worse mistake bound, it has slightly worse memory requirements, but the trade-off is it doubles the kind of set of functions it can express just by this one trick. Questions about balanced Winnow? So let me just step back up the stack here. We looked at two algorithms that look suspiciously very similar. Both of them are online mistake-driven algorithms. Both of them, at least in the vanilla version, the algorithms proceed as follows. It's a series of rounds. An example comes in, you make a prediction. If there's a mistake, you make an update. Perceptron is, and both of them are actually fairly robust and are used quite a bit in the wild. Perceptron more than the Winnow algorithm, and I'm not sure why. So now the question is, what should you use? How should you know which algorithm to use based on what should you decide whether to use a perceptron algorithm? And one guiding factor is you use the multiplicative update if you believe that your true concept is a sparse function. You use the additive update if you don't have any such faith, you don't know you don't have any hope that only a small number of features are relevant, and so you expect your final weight vector to be a dense vector. And in that case, you use the additive update. There is this one other little tweak. If every example itself is sparse, but your final weight vector is dense, then it turns out there's this very cool update rule which is called addagrad, which was invented not more than say 5 or 6 years ago, which fits that bill. So perceptron works. Perceptron is the best thing to do when your examples are dense and your true weight vector is also a dense vector. What's a dense vector? Basically the number of non-zero entries dominates. Winnow is the right algorithm to use if your true weight vector is sparse. And there are other regimes where your true weight vector could be dense, but each example itself is sparse, and we'll probably get to those once towards the end of, maybe in the second half of the semester, when we're talking about support vector machines.
Question?
Yes?
Is there ever a time where you might use, say, Winnow first to get rid of features and then use Perceptron to...
It's not a bad idea actually. I've never tried it myself, but it might be useful. That's actually a good idea. So the suggestion was, what if you run Winnow first, then let it run and then discover what are the relevant features, and then somehow threshold out all the low weights, keep only relevant features, and then run Perceptron. But the point is, once you've run Winnow, you already have your classifier. So why do you need the second round of training? What might be interesting is if you want to discover what are relevant features. But if you only care about the classifier, then you're done. You've solved the problem.
Could the unrelevant features be counted as noise?
They are noise.
Okay, yeah, I guess.
Yes. In fact, maybe you'll see a case in one of your homeworks in the future where I'll probably throw in thousands of irrelevant features and only change those. And performance will decrease because your dimensionality increases. Your classifier will get worse if your irrelevant features dominate.
So running on the Winnow first, you would find the relevant features, and so when you be able to get something slightly different, just running on the relevant features.
Yeah, but you know, if you stop making mistakes, if you hit the mistake bound, you've learned your classifier. Remember that all of this, the unstated assumption in any of these things is that we are assuming that the true concept is linearly separate.
Okay.
The reason why in practice people use these, people use perceptron or the average perceptron and things like that is because we have no such guarantees. If we know without doubt that our true concept is linearly separable, then we are in a very, very lucky, slightly suspicious situation. Other questions? Right, so let me wrap up this whole lecture on Winnow. We have seen a multiplicative update rule, and it's important to realize that it still learns a linear classifier. We are still in the world of linear classifiers, we'll be in the world of linear classifiers for quite a while. And the multiplicative update has a very cool property that the mistake bound only depends on the number of relevant features. The other thing is we can have other generalizations. Who said that multiplying and dividing by 2 is the right thing to do? You can multiply and divide by another number, and those things are part of you generally see those things. In fact, those are the standard versions of Winnow, where that other tiny number that you multiply and divide by is something like the learning rate in your perceptron, and it decides how fast the algorithm converges. Questions about the Winnow algorithm? How are we on time? We have 2 minutes. So I'm not going to start computational learning theory because that's going to be at least 2 weeks of lecture, and 2 minutes is certainly not enough. So just to give you a heads up of what's coming up, we've come to the end of this whole discussion on online algorithms. We are still in this, a lot of pretty much this entire semester's class will be driven by this need to define what is learnability. How do you mathematically define whether a function can be learned or not? One way in which we define learnability is the mistake bound. We claim that a function is learnable if there is a classifier that will stop making mistakes. That's not the only way of defining learnability, and starting in the next lecture we'll look at another style of defining learnability, which is called batch learnability, where we'll define a concept to be learnable. If given a finite set of examples, we will make very few errors, not zero, but very few errors on future examples. So we'll define learnability by how well our classifiers do in the future, rather than just counting number of mistakes. This style of analysis gives rise to pretty much many of the dominant learning algorithms that we've seen. So it's one of my favorite parts of machine learning, so do show up and it's going to be fun. And a reminder about homeworks, midterms and all those things, they still stand.
What?